So now let's see these features in action in a simple Hello World program. First, I'll open and close my main program scope. Then I'll ensure that all variables must have an explicitly declared type. And now I'm going to define a constant that I'll use to define the length of the greetings that I'll define. Let's make them 30 characters long. And I'm going to make my greeting coarray allocatable. In most cases, unfortunately, when you make a variable allocatable, it obligates the compiler to handle all memory allocations and deallocations for you. In this case, we are going to do an explicit allocation, but the compiler will handle freeing the memory for us, so we won't write an explicit deallocation. The language standard requires that I not specify the size of this allocation. What's going to happen is that size will get set either at compile time through a flag that I can pass, or I can override that value at program startup with an environment variable. The coarray that we've defined here locally, if we drop the square braces, will look like a scalar. So it's actually referred to as a scalar coarray. And if it were locally an array, then it would be referred to as an array coarray. Now we're going to do what's referred to as internal file input-output, internal file I/O, where I'm basically going to write into this string. Like any other write statement, I'll have to have a format. My format is going to be twice repeated character output followed by a 2-digit integer. Here's the first character output. And I'm calling now an intrinsic function built into the language that will tell me which image is executing this line of code. More character output. And now I'm calling an intrinsic procedure that will tell me how many images are running. Now that we've allocated this memory and written into it, we need to make sure that everyone has gotten to this point before we actually try to access it from another image. We do that with the sync all statement. Now I'll have image 1 handle the printing. But I'm not concerned about the ordering of the printing, so I can use the doConcurrent construct to communicate to the compiler that ordering doesn't matter here. We'll loop from 1 to the number of images. And one of the nice things about the one-sided communication model of Fortran 2008 is that I can just go out and grab the data I need from the image that has it on the fly. So now we'll compile this with the Intel compiler, and we'll pass a flag that tells it we're running in shared memory. We could also run the same code with a higher level of licensing in distributed memory. And we'll let the compiler know here how many images we want to use. When we run the code, we see that the statements come out sequentially. This gets back to this philosophy of communicating to the compiler the opportunity for concurrency with that doConcurrent loop, but not mandating that the compiler exploit it if it doesn't make sense to do so for what we're doing, in this case just simple I/O. So let's see what happens if we comment out these two print statements. So now we're effectively doing an all-to-all communication. every image will go out and grab the data and print. Now, every time we run it, we'll see things come out in a different and non-deterministic order. So we can see from this example how simple it is to go from a gather operation, bringing all the data to one image, to an all-to-all communication where every image is going out and grabbing data from each other image, and each one does it on the fly inside the print statement.